Hello guys, my name is Utsav Yadav and I am here again with the new topic of data science is preparing to model the data. With the help of these key points, today we understand the topic preparing to model data in data science. So we go through the point the story so far. Before diving into the actual modeling process, it is essential to understand the current state of your data, what steps you have already taken, and what challenges might lie ahead. This section focuses on summarizing the overall data preparation process and highlighting key findings or issues you have encountered up to this point. Typically, the story so far includes data exploration, data cleaning, feature engineering, problem farming. Summarizing key insight from exploratory data analysis EDA, such as distribution trends, correlation, and any anomalies found in the data. Data cleaning. Describing the steps taken to clean the data, including handling missing values, removing outliers, dealing with duplicates, and fixing any inconsistencies in the dataset. Feature engineering. A recap of the feature creation or transformation that have been done, such as encoding categorical variables, scaling numerical values, or creating new features from existing ones. Problem framing. Clearly stating the problem you are trying to solve with modeling, whether it's a classification, regression, clustering, or other machine learning problem. Now, we have second point, partitioning the data. Data partitioning is a critical step in preparing to model the data. It involves splitting the dataset into subsets that will be used to train, validate, and test the model. A well-partitioned dataset ensures that the model is trained on one portion of the data and evaluated on another, preventing overfitting and providing a realistic estimate of model performance on unseen data. Common approaches for partitioning data is training set, validation set, test set, etc. First, training set. This is the largest portion of your data, typically 60 to 80%, and it is used to train the model. The model learns from this subset validation set. Usually 10 to 20% of the data, the validation set is used to fine tune the model during training, allowing for hyperparameter turning and model selection. It helps in making decision about which model is best and provides a way to prevent overfitting. Test set. The remaining 10 to 20% of the data is used only to access the final model's performance. This set should never be used during training or validation to ensure an unbiased performance. So, with the help of the PDF, we see we see how to run partition the data in Python programming language. This is the code by which we can make the partition of data. The command create two dataset bank train and bank test. While the name of the data set are arbitrary, the test data set is always the second one created. The first input bank specified that we are partitioning the bank dataset, and the test type equal to 0.25 input state that 25% of the bank data should be in the test dataset, while the remaining 75% should be in the training dataset. The random state input set the seed for the random number generator that will randomly split the data into training and test data sets. The input value itself is arbitrary. The important thing is to specify the seed and use the same number when you want to replicate your results. Setting the random seed will ensure you will get the same answer as before. To confirm that the data sets were partitioned correctly, you can compare the shapes of the original training and test that data set using the shape feature. And guys, this is the programming this now techniques for partitioning data. The techniques for partitioning data are random split technique, stratified split technique, k-fold cross validation technique. Random split randomly split the data into the three set: training, validation, test. Stratified split Ensure that each split has a similar distribution of classes or categories as the original dataset. Especially important in the classification problem with imbalanced classes. K-fold cross-validation splits the data into K subsets. The model is trained on K1 folds and tested on the remaining fold. This process is repeated K times, each time with a different fold as the test set. This technique helps to make better use of the data and reduces the variance of performance estimate. Validation your partition. Once the data is partitioned, the next step is to validate the partitions to ensure they reflect the original data distribution and contain representative samples. Validation steps include check for data leakage, check for representative time series data validations. Check for data leakage. Ensure that there is no overlap between training, validation, and test sets. Any leakage can result in overlay optimistic performance estimates as the model might indirectly see data it will later be tested on. Check for representativeness. Verify that each partition contains a proportional representation of the key characteristic of the dataset, such as class distribution in the classification problem or the range of numerical values in a regression problem. For instance, if you have a skewed class distribution, you may want to use stratified sampling to ensure that each partition has a similar class distribution. Time series data validation. If the data has temporal component, example stock prices, weather data, you cannot randomly split the data. In this case, you might use a time series split where earlier data is used for training and later data is used for testing. This ensures that no future data is used to predict the past. In summary, validation the partition ensures that the splits accurately reflect the problem you are trying to solve and that there is no inadvertent bias or data leakage. Fourth, balancing the training dataset. In many real world datasets, especially those involving classification tasks, the training data may be imbalanced. Example, significantly more samples of one class than other. This imbalance can lead to biased models that perform poorly on the monitoring class. Techniques to handle imbalanced datasets. Resampling techniques are oversampling and undersampling. Increase the number of samples in the minority class, typically through techniques like SMOD, synthetic minority oversampling technique, which generates synthetic examples. Undersampling. Reduce the number of samples in the majority class to balance the dataset. Class weight. Some algorithms allow you to assign higher weights to the minority class during training, thus penalize the model for making incorrect prediction on the minority class. Anomaly detection. In some cases where the imbalance is extreme, the problem might be treated as an anomaly detection problem where the focus is on correctly identifying the rare class. Ensemble methods. Using ensemble method like random forest or boost can help manage the imbalance classes. Whereas these methods are more robust to class imbalance due to their use of multiple decision trees. Balancing the dataset help ensure that the model does not become biased towards predicting the majority class and is able to generalize well on the minority class. Establishing baseline model performance. Before jumping into building complex model, it is important to establish a baseline. A baseline model represents the minimum level of performance you should accept for a model, and it gives you a reference point to compare more sophisticated models. Some approaches to establish a baseline. Simple models. This could be very basic model like a dummy classifier, regressor, logistic regression, linear regression. Performance matrices. Use appropriate performance matrices based on your problem. For example, classification, accuracy, precision, recall, F1 score, ROC, AUC, etc. Regression, mean absolute error, mean square error, and R square score, etc. Random prediction. For some problems, you can establish a baseline by predicting randomly based on the distribution of the class or continuous values. Comparing with domain knowledge, in some cases, you might have domain knowledge or expert insight that can help you set a reasonable baseline. For example, in medical diagnosis, you might assume a model should be able to predict certain condition with a known baseline accuracy based on a prior research. By establishing a baseline, you have benchmark against which you can compare more complex models. It also helps identify if the model you are building is significantly better or if it's underperforming compared to a trial approach. Now we go through the summary of our topic, which is preparing to the model data. The process of preparing data for modeling involves multiple set steps that are crucial for ensuring model quality and performance. The story so far provide a summary of the data and preparation made so far. Partitioning the data involves splitting data into training, validation, and test sets using various strategies to avoid overfitting and ensure robustness. Validating your partition ensures that your data splits are meaningful and prevent issues like data leakage or misrepresentation of the dataset. Balancing the training dataset addresses a class imbalance which could lead to the biased model if not managed properly. Establishing baseline model performance give a reference point to evaluate how well more sophisticated models are performing. So guys, today we fully understand the topic of preparing to model the data in our video. So if you find this video helpful, like our video, subscribe our channel and share this video to your friends. Thank you.